In modern symmetric key ciphers, Shannon's impossibility theorem means that the only method for guaranteeing information theoretically secure encryption of a message is the one-time pad. However, this requires a key sequence of the same length as the message. Developments in quantum Shannon information theory have made it possible to remove this drawback of the one-time pad. This paper presents a design for a quantum stream cipher that uses quantum Shannon information theory to encrypt messages of any length with information theoretically secure encryption using a very short key. Let's explain Shannon's impossibility theorem. Shannon proved that against a ciphertext-only attack, the information theoretic security of a message is less than the entropy of the key. This is his impossibility theorem. As a result, to make any message information theoretically secure, a one-time pad is required. To avoid such inefficient encryption, it is necessary to invalidate Shannon's impossibility theorem. Quantum Shannon information theory began in the 1960s with the construction of quantum communication theory by Hellstrom, Holovo, Ewan, and others. The results of their work have since been applied to cryptography. The forbidden principle in quantum systems plays an important role. It states that signals with non-orthogonal states cannot be distinguished without error. The theory that quantitatively evaluates this principle is called quantum detection theory. Its fundamental theorem was formulated by Hellstrom, Holovo, Ewan, and others. Error caused by quantum noise can be controlled by measuring the quantum state of the received signal described by decision operator pi. Ewan proposed an attempt to apply quantum Shannon information theory to cryptography. This is the concept of keyed communication in quantum noise. This means that a receiver with a key has better reception performance than a receiver without a key. This is called advantage creation. The encryption realized using this is called a quantum stream cipher. This diagram shows the fundamental configuration of quantum stream ciphers. The sender prepares M communication bases. One communication basis is randomly selected using a short secret key and the output sequence of a pseudo-random number generator that expands it. Binary information is transmitted using the selected communication basis. The authorized receiver uses the same running key sequence as the sender to provide the optimal signal rotation for receiving the communication basis selected by the sender and performs quantum measurements for the corresponding binary value. This allows accurate communication information to be obtained. An eavesdropper must identify the two M signals transmitted by the M bases. In this case, quantum noise will significantly increase the error. In other words, the signal received by the eavesdropper is completely randomized by quantum noise. An eavesdropper would attempt an attack on the optical fiber communication line. The eavesdropper would need to realize all quantum measurements allowed by quantum mechanics, and would need to use a computer with infinite power. Research is also underway to implement the information theoretically secure quantum stream cipher described here. Since the realization of a handmade experimental device in 2002, commercial transceivers are currently being developed. Those interested in further details are welcome to read the full paper.